All right, this video will hopefully show you how to design a rocket in OpenRocket. OpenRocket is free software available online. You do need the proper version of Java to make your OpenRocket work on your computer, so you might have to play around with it. This assumes you've opened OpenRocket, and you should see a window that looks like this. We're going to start with the nose cone. Just click on nose cone, it appears here in this window, and the visual is right here. And this red dot here is your center of pressure, and the blue dot here is your center of gravity, and there you're going to see those shift around as we build the rocket. Okay. So the nose cone in our case is that we're going to use for this build is called a BT80, and it's way at the bottom of the database. Now you can enter in the numbers manually, or you can find it on the list. This one calls it a BNC80K. It's an OGIV. This is the shape of the nose cone, and ours is 6.6 centimeters in diameter, and it's 20.8 centimeters in length. So once you do that, you see the shape change. Now you've got to go in and change a couple things here. I don't think this BNC is exactly what we're working with this year. So let's try a couple things. This looks good. Wall thickness is definitely not 3 centimeters. So wall thickness would be about, well, first of all, it's not filled. There we go. And wall thickness would probably be 2 millimeters or 0.2. It's not balsa. It is, the closest here would be maybe PVC. It's some kind of plastic nose cone. It has a shoulder on it. A shoulder in our case is 4 centimeters, and the thickness, it is end capped. The thickness we're going to make 0.2 again. Okay, and I think that's good for the nose cone. Next component would be the body tube. Click on body tube. Again, we're dealing with a BT80 body tube, and the BT80 is 45 centimeters long in our case, and 6.6 centimeters in diameter. So you can manually enter in those numbers, or you can look for the model that you purchased. And it's good to have your components on the desk with you with a ruler. So there's a BT80, 6.6 and 46 centimeters. Let's use it. Okay, now you can go in and manually override any of those sets. The rest looks good. So it's not filled, it's a hollow tube, and let's stick with that for now. Okay, now you can lengthen this tube. You can double click on it, and you can lengthen this tube. If you put a coupler in your tube, later you can make your tube as long or as short as you want. And we're going to keep an eye as we build. We're going to keep an eye on this stability number over here on the right. So now we're at -2. So that's obviously unstable. There's no wings on it. So we want to bring that up to 1 or 2 cal. And that's calculated from the surface area of the rocket and the center of gravity and the center of pressure. Some kind of algorithm built into the sim. So next component would be a motor mount. Let's put a motor mount in it. So you make sure your body tube is selected, and then these other icons are going to light up. So we're able to put an inner tube in there, and under motor, you tell the sim that this is going to be your motor mount. And now you can add cluster motor mounts, which are really cool, a little more complex for launch in here. You can do other more complex things you can play around with, but let's stick with one motor mount for now. The motor mounts that we're going to use in this case are a 24 millimeter. So that's 2.4 centimeters, and you can see it change there. And we'll go with the inner diameter of 2.3. The length in our case is, I believe, 8 centimeters. So then you would just change that to 8 or 8.2 to be exact. Okay, and we're going to sink it into the body a little bit. So relative position of -1, that's just going to be under that. And making sure that's a motor mount. Good. Okay, next thing we're going to put on this is centering rings. So the centering rings help the motor mount stay in place. They are not cardboard. They are going to be probably a birch plywood or a maple plywood, so a thin plywood, about 3 millimeters. And you want to have it sitting around there, flush with the motor mount, or just a little bit in is fine. Okay, now this is a single stage rocket in this case. If it's a dual stage, if it has a booster stage, you need to leave some space right here at the end of your body tube for a coupler to fit that booster stage behind this motor. So keep that in mind if you're building a second stage. Centering ring, if you have automatic selected, it will sort of fit that centering ring right around your motor mount. Let's add a second centering ring. And these centering rings, they secure the motor mount so that when you launch the rocket, your motor mount just doesn't launch right through your rocket. The whole thing is carried with. Okay, 6.5. Oh, let's see here. Let's bring that in there. Okay. Thickness is 0.2, and now that motor mount looks a little more secure. It's held in place by 2 centering rings. Okay. All right, next thing we want to add are wings. So the wings are going to go on the body tube. So you have body tube selected, and then you can choose from these wings here. We're just going to go with trapezoidal. I am going to put 3 wings on this one. You can put up to 8 wings, which look really cool. I think it's harder to build. It might not fly as well, but you give it a try. Let's go with 3 for now. You can change the root cord, which makes them a little bit bigger. And then the tip cord there you can mess around with. Height. Okay, so let's make the height 4 centimeters. And you can make whatever wing size you want. You can modify it later. You just want to keep an eye on the stability number. So now our stability is up to 1.5. I see different numbers being the ideal online. I think if it's between 1 and 1.5, it's probably good. And you want to make sure that your center of gravity is ahead of your center of pressure. Yeah. Okay, so let's change the shape of your fins. There's a couple ways to do it. You can change this angle here. And then you can also move your fins on the body itself. So let's stick them about there. I like to have the fins sticking below the body tube so that you can actually set the rocket on the ground. It doesn't fall over. It sits on the launch pad nicely, or just sits on the desk nicely too. Okay, the fins are not cardboard. The fins are going to be that same plywood. So birch ply or a maple ply. And their thickness, 3 or 4 mil. So let's go with 4 mil. Fin tabs are going to help mount your fins to the body. So fin tabs, if you click calculate automatically, the fin tab will extend from the fin into the body tube. So we're going to be cutting slots in the side of that body tube, and the fin tab is going to insert right in and touch that inner motor mount. So that's going to allow for, well, it's going to make the fins much stronger. So you're going to glue the surface right there, and all the way along the body tube. Okay, now you see your stability change again because the weight's changed. We're going to add inside the body tube, we're going to throw a parachute. So this is parachute is, I think, about 50 centimeters diameter. You can change things like the string even, and this affects the weight, which will affect our flight simulation later. So we're going to give it plastic, and sure, go in and change the thread, and then we can change what it looks like in the simulation. So a parachute will be probably about that big, and we're going to move it into the body of the rocket. It's going to sit around there. Okay, you also need, in that body tube, we're going to put a shock cord, and the shock cord, let's change what it looks like. It takes up a bit of space again, and that's fine for material. I usually put about 1 meter of shock cord inside a rocket, so 100 centimeters, and it might sit up there. Okay, now under motors, you could add an engine block as well. We're going to go though right to motors. Make sure that your inner tube is selected. That's where your motor is going to go. Click New Configuration, and under that icon, we're going to put a D motor in just for this trial. It has to be 24 millimeters in diameter because that is the size of our motor mount. So let's try D12. And you can check with your the place you're going to order the motors from. Make sure that these motors are actually available. 74 millimeter by, or 24 millimeter by 70, and a D12. Now you can select the ejection charge here. So 3 seconds, 5, or 7, and that means how many seconds after motor burnout is the engine going to inject that parachute out. So you don't want it happening immediately. You want the rocket to coast a little ways to get up to the apogee, and then that parachute should be ejected. If it's too early, it's going to stop the flight. If it's too late, the rocket could crash on the ground and then eject the parachute. So you want an ideal time here. Anything that's 24 millimeters will work, as long as it's not too long either. So you got to keep an eye on the length, and you have to be able to purchase these motors. So you could go up to an E or an F motor, but let's try a D for this simulation. Okay, we've got our motor selected, and then we go to Flight Sim. So here we go under Flight Simulation, Run Sim, and you're going to get some data. So optimum delay is 4 seconds, and it tells you velocity. It gives you a green light, which means it is stable. There's no warnings, and it even tells you your calculated flight time. So we could plot a graph of this under Plot, and you hit Plot again. Now you can select a whole bunch of different things under here that you want to see, and you get a pretty cool looking graph that tells you approximately how high it will go when the device, it says recovery device deployment. So this is your ejection charge right here when your parachute came out, which is pretty much ideal. You want that right around there. Looks like a good stable flight. Now you can go in and modify your fin size and your body tube length, anything else that you want to change, and then the motor even, and then run a simulation again and shoot for that ideal flight. Ooh, stability dropped down low, so we might have to go in and do some more work on that. Okay, that's it for now.